Hello, class. I'm back. I want to do a lecture. This is actually one of my favorite lectures to do. I like comparing and showing the comparison between the three different types of torsion rods that you would come in contact with throughout your lives, and of course, let's just draw these. I'm gonna crosshatch them a little bit and actually give them some three-dimensionality. So that would be the solid torsion rod. Now, to transmit the same torque, right? All of these are going to be, they're torsion rods, so they're going to be transmitting torque, right? We've got one end of them that's going to be turning with whatever it is. Like think of the tailgate of a truck, right? If it had a torsion rod in it, it would, as it torqued, it would take up as a spring some of that force. So it'd be easier to put the truck up. That's sort of how I look at it. But torsion rods, invade everything that we do. So we've got a torque rod. Now, I'll give you another example. How about a ship's propeller, right? That's a torsion rod. Ship's propeller would be a torsion rod. How about the crankshaft in your car? How about any motor? How about the fan in your room that's turning around? Doesn't that have a torsion rod in there that's turning around with it? Isn't the wind of the air? How about the rod that is connected to the windmill that is connected to the generator that's making the power that we use for electricity? Right, so there's the torsion rods or rods in general that are under a torque loading, right? This is our torque loading. Are in pure shear, whether it's a solid or, now to carry that same torque, I would have to have a larger hollow. I'm going to draw it like that. That wasn't very good. I'll try and clean that up. I'm going to have a hollow torsion rod. Why would I want to do that? Well, the reason I'd want to do that, and we're going to see in my example in the comparison of solid and hollow and thin-walled torsion shafts, that you're going to save material, right? You're going to save material in the cross section if you make it hollow, or, I mean, if you can make it hollow. There are other considerations, like I mentioned before, the crankshaft in your car. Obviously, you don't have the space, requirements to really get anything except for a solid torsion rod inside the motor. I mean, think of how big your motor would be. The motor's already big enough. So we have to have a solid cross section. Plus, we have other forces on the crankshaft in your car when the pistons are coming down. There are flexural forces as well as torsional forces. So that's another aspect to having a solid shaft. For the drive shaft in your car, you easily, in fact, you do have a hollow shaft. And so when I say hollow shaft, and the comparison I'm going to make here is I'm going to say that if we looked at the two radii, the inner radii and the outer radii, that the inner radii would be approximately, in this case, is going to be approximately 0.8 of the outer radius, so that we have that relationship. And that's very standard. And that is approximately the case for your drive shaft in your car. If you ever cut a drive shaft in a car in half, that stops people from going anywhere. Yes. Anyway, that's two. Now, I want to look at a third. I'm going to draw this even larger. And in fact, I'm drawing it probably pretty much to scale, compared to the other two, as you're going to see. Because, of course, I already know what the answer is because I've done this comparison before. Now, when we look at this and we're looking at the outer radius, right, for a thin walled tube. Now this is a hollow cylinder, right? And we have equations for the polar moment of inertia for a hollow cylinder. In fact, we have equations for the polar moment of inertia for a solid cylinder. Let's put that up there. And we have polar moment of inertia for a hollow cylinder, which would be R outer to the fourth minus R inner to the fourth. And then we also have J. I don't really have any room on the side there. I'll just put it underneath. We also have J for a thin walled tube, which is 2 pi R outer cubed times T. And basically what we're saying is we're putting all of the area out here. And when we talk about a thin walled tube, we usually are thinking that T is approximately is less than or equal to about 5%. That's a 5% of the outer radius, right? So those are the relationships that I'm going to be using when I do an analysis between the various different torsion rod cross sections that we can have. And really, if you think about it, because nobody's going to make a torsion rod that's rectangular. So we're talking about basically the 3 different types of torsion rods that you're ever going to come into contact with in your life, and how do the cross-sectional areas compare for the same torque being applied to them. Now, there's 2 things that are common. First of all, I'm going to say that, okay, we want the same torque. So we're going to apply the same torque to all 3 of these. That's the comparison. And doesn't that make sense? Because we're trying to compare apples against apples, right? So we're comparing the same torque loading on that as I've got on here. Oh boy, that was a T, as I've got on here. So same torque and same material. So in other words, tau max is going to be the same, right? I'm using steel or aluminum or whatever it is, but I'm using the same material. I should put that there. So same, I mean, because we're trying to compare apples to apples. So same material for all 3 of these cross sections, which means the same maximum shear stress. And I'm going to put the same torque under all 3 of these. And then after I find out how they compare, we've got the same torque, same material that I'm using for all 3 of them, then I'm going to say, hey, well, now that I found out what the outer radius is for all 3 of these, let's figure out what the cross-sectional area is and the material savings for all 3 of these. Because really, when I say the same torque and I say the same material that I'm using, I'm implying that I've got the same job for all 3 of these, right? Now, there might be other considerations, but this would be one of the main considerations. How much material, because the material cost is proportional. I mean, if I'm going to buy steel, I'm going to buy it by the pound, right? Or by the kilogram, which on the surface of the earth would be interchangeable, right? So if I can buy less and do the same thing with less, that's a direct cost savings. So let's look at how they compare, all right? So like I said, what I want to do is I want to compare apples to apples. So we're going to compare the maximum shear stress divided by the torque. Maximum shear stress divided by the torque. Let's just write down our equations here. So maximum shear stress equals TR over J. right? That's one of our equations. That's our equation for maximum shear stress, figuring out the maximum shear stress. If we know the torque, we know the outside radius, and we know what J is for that cross section. When we know J for all those cross sections right now. Anyway, it's a J. So if we, that is one of ours. And the second one is that the angle of inclination or the angle of rotation, whatever you want to call it, twist. A lot of times people call it angle of twist. TL over JG. Right? I try to give you all the terminology that people are using out there so that when you run into it, when you get out, you'll know what it is. Okay, so we've got those two equations. So we've got this. We want to compare same material, same torque, right? So if we solve that for all three of the equations, let's see. Max over T gives me R sub 0 over J, right? So all three of these would be R outer over J, whatever the J is for that particular cross section. So for the solid cross section, that would be R outer, right? Like they all have, divided by pi R outer to the fourth. I better put an S there because that's the solid shaft, times 2. I hope I didn't lose anybody on that algebra. I'm just really substituting in J from the bottom, pi R squared over 2. So it's upside down. And of course, as I simplify this, I'm going to get 2 divided by pi R outer of the solid shaft cubed, right? Everybody can see that that's going to cancel out with one of those, and so that's what I end up getting. All right, let's do the same thing. So this is for the, that's for the solid shaft. Right? Actually, I should put equals. Well, no, I have the solid shaft right there. All right, and I can use these equal signs because I'm still looking at tau max over T. So I'm comparing these, right? Excuse me. That's the great thing about remote learning. I just didn't give anybody COVID accidentally. You know, I'm kidding. I certainly hope nobody does who's at Wentworth get COVID, either the faculty, the staff, or the students, but I wasn't going back there. All right, now, if we do this with the hollow shaft, I get the same thing, 2 times the outer diameter of the hollow shaft divided by pi times R outer of the hollow shaft to the fourth minus R inner of the hollow shaft to the fourth, right? So that's our second one. That's for our hollow shaft. And how about if I do it for the thin-walled torsion shaft? You know, all of these, I should have drawn these all in 3-dimensional. Oh, look at that. There you go. That's a hollow torsion shaft. If you ever saw one. Or no, that's a thin wall. This is a hollow torsion shaft now, if I ever saw one. That's a thin wall torsion shaft if I ever saw one. Yeah, I don't know how else I would draw that. It looks right, I guess. All right, now the last one, we've got the same thing. This is going to be, but this is a little different because we have our outer of the thin-walled shaft divided by 2 pi R outer to the third of the thin-walled shaft times T. And I want to simplify that. I'll simplify that in just a second so that we can, because we're using 0.5, right? But right now I didn't want to put those in. I wanted these to be our 3 equations that we're going to now compare. And and I'm going to put the comparisons in now. So we've got 2 over pi r outer of the solid shaft cubed, right? Times pi. Sorry, forgot the pi. And that, now we're going to actually make some things here. Now, we want to talk about r outer, so 2 times r outer of the hollow shaft divided by, now what I want to do is substitute in here. So pi, and then r outer of the hollow shaft, r inner of the hollow shaft is 0.8, right? So it's going to be r outer of the hollow shaft squared, or to the 4th, excuse me, to the 4th, minus 0.8 to the 4th times r outer of the hollow shaft to the 4th, right? And I should put brackets here rather than, because I've already got parentheses inside there. I'll extend that a little bit. Now, what is 0.8 to the 4th? And I think everybody knows that 0.8 to the 4th is 0.59. I'm just going to do that for a second. 0.8 to the 4th equals, well, no, it's 0.4096. Is that right? 0.4096. Let me just look here. I have no idea. No, yeah, that would probably be 0.8 to the 4th. Yeah, I get 0.4096. All right. So let's do that. So we've got 2, and then I can, well, I'll do it. Right? That's the r outer, so that nobody feels lost in the steps that I'm doing here. And then I'm going to bring pi, and I'm going to bring r outer to the 4th out of there. R outer, right, hollow to the 4th. And then I'll just say this, I won't need it. It'll be parentheses. I won't So if I take that out of there, that's going to give me 1 minus 0.4096. Right, does everybody see that? Now what I can do is I can cross this out, and I can cross one of those out, and that gives me cubed. And I know that 1 minus 0.4096 equals a number. So, wait, what? Oh my God, I put that way over there. People are going to think that that's pi cubed, and of course it's not. No, 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 no. Yeah, that is not pi cubed. Let's put the cube, because I just crossed that out. I'll put the cube over here. I think everybody can see that now that I've just crossed the 4 out and put the 3 there. So I want to do this. So 2 divided by pi. Let's just come up with an actual number here. 2 divided by pi divided by 1 minus 0.4096 equals 1.0783. I actually gave you 5 significant digits there. Divided by r outer of the hollow cubed. All right. You know, we could do that here too. We could say that for the solid, 2 over pi, so 2 divided by pi, 0.63662. So 0.63662 divided by the outer radius of the solid cubed is going to equal 1.0783 over the outer radius of the hollow thing cubed. And then we're still working on this idea here where we're looking at, we're comparing the maximum here divided by t. And so we're going to be looking at this one too. And, you know, just going along here. So this gives me r outer of the thin-walled divided by 2 pi times r outer of the thin-walled cubed times 0.05, right? Because what T is 0.05 or 5% of the outer thin-walled torsion rod, right? And so this is what we end up getting, and then we can simplify this because, well, I can do the number right now. Why don't we put that up top? I hope that I might want to double check 1 divided by, I know what the answer is supposed to be, but I'm sort of going a little different route here with you. 2 divided by pi divided by 0.05, and that gives me 3.1831. 3.1831 divided by, and then of course that is going to cancel out with one of the, well, actually it'll cancel out with this one. Why don't we do that and leave that? Fine, that's still a 3. And then that'll be R outer of the thin walled tube. So we can now compare how the radii of these individual things are going to compare. And so what I want to do is just take the reciprocal of this, right? So that I end up with R outer solid. That's what I'm going to end up with. I'm going to take the reciprocal of this and then take the cube root of that. I hope I'm going to write it. I'm going to actually write it here. This is going to be the cube root of R outside cubed divided by 0.63662. Right? Everybody see what I'm doing there and how I'm now getting the outer, radius or whatever. Just a comparison. So all I'm doing is I'm going to flip these numbers over and take the cube root so that I end up getting a coefficient in front of this instead, but the coefficient that would just be for that. I probably should have done that in 2 steps for you, but I think everybody can sort of see what I'm doing to get ROS, because I take the cube root of that, and then I take the cube root of that, and of course that's the reciprocal of this, so it shouldn't be any problems. I hope. So 0.63662 taken to the reciprocal, and then the cube root of that, I get 1.16. So 1.16, I'll actually get 24, right? R outer equals, now let's do the same thing to this. Just going to take the reciprocal, take the cube root. So 1.0783 to the reciprocal, and then to the cube root gives me 0.97518. R outer of the, I hope I can get the next one in there, of the hollow torsion rod. And then the last one I've got is, let me just see. Oh, wait, this should be cubed. Yes. I'm sorry about that. You were probably, everybody was saying, hey, that should be cubed, but I couldn't hear you. But anyway, we did get the cube there in time. So 3.1831 to the reciprocal taken to the cube root equals 0.67983. 0.67981. Okay, times I R of the thin-walled tube. All right, now I am going to normalize all of those just in a second. I just want to make sure that they all are coming out exactly right. I'm going to just pause you for a second. Hello, class. I am back. It was only like 5 seconds. I checked 2 of the things out, and of course, they worked out perfectly. I can't always say that because I actually did this in sort of a more robust and straightforward manner using less algebra steps than I normally would for you, I know, but that's because you're so much smarter. And I know that everybody could follow me, along through these 3 steps. And it did work out. And what I want to do is I want to compare them to the outer radius of the solid shaft. So let's say, let's just do the comparison, and then we actually come up with, let's say, an outer diameter of a shaft and see how they would actually compare. So when we look out the outer radius of this in terms of the hollow shaft, it'd be 0.9758. Have I got this right? Yeah. Yeah. 0.9758 divided by 1.124. So the radius of the solid shaft is going to be 0.838, the outside radius of the hollow shaft, right? Does everyone see that? Because the outside radius of that would be 0.7 divided by that. Same thing would be true with this. The outside radius of the hollow shaft. Wait, have I? No, I've got that backwards. Oh, no, that's right. That is right. I'm sorry. Okay, I'm going to do this, though, because on my paper here, which that is exactly right, I'm going to do it the other way, too. So the outside radius of the hollow shaft is going to be 1.19 times the radius of the solid shaft. So about 20% larger, right? And you can see it's about 20% larger. So the hollow shaft, okay, same material, steel, same torque. Okay, same torque, same material. This thing is 20%. Hollow, 20% larger radius, right? 20%. We're going to compare the areas too there in a second, right? Now, how about the thin-walled tube? If we look at the outer radius of the thin-walled tube compared to the solid tube, I get 1.7 times the radius of the solid. We could figure it out for the thin-walled tube, for the hollow, but who cares? We're really comparing everything to the solid. So that's 70%. So 70% larger. So ROTW is 70% larger. Wow. That's pretty large, isn't it? So it's larger when we go with the thin-walled tube than if we go with the hollow tube. Hollow tube's 20% larger. The thin-walled tube outer diameter is going to be 70% larger. Now let's look at the cross-sectional areas of the 3 of them. So if we look at the cross-sectional area of our outer solid squared, that's what it's going to be. It's going to be, 3.14 times our outer squared. That's the cross-sectional area for the solid. And what is the cross-sectional area for the hollow? Well, the cross-sectional area for the hollow is going to be pi times r outer of the hollow squared minus r inner. Well, actually, why don't we make it r? I'll do it r inner of the hollow squared, and I'll write the next thing too. So pi, so everybody sees what I'm doing. R outer of the hollow squared minus, we know that it's 0.8, right? So it's 0.8, but this time instead of to the fourth, it's just squared, isn't it? R outer of the hollow squared. So that's what we've got there. That should be R inner, because I wrote it there. Yeah, it's not R outer, it's R inner. So we've got this, and 0.8 squared is 0.64, isn't it? So if I were to, just continue this, I'll just go like that. If I continue this down here, I really have pi times r outer of the hollow cylinder squared times 1 minus 0.64. Does everyone see that? Right? 1 minus 0.64 is 0.36. So I could say that down here, what I really have is 0.36 times pi. Let's just do that. So 0.36 times pi is 1.131. 1.131 r outer squared, and we want to equate that to 3.1416 r outer of the solid shaft squared, right? Because that represents the area for the solid shaft. This represents the area for the hollow shaft. You want to do the same thing and look at the area of the thin-walled shaft. The area of a thin-walled shaft, that's just the perimeter, 2 pi r times the thickness. So 2 pi r outer thin-walled times 0.05, the thickness, right? I should have maybe written that anyway. Not a lot of room. Times 0.05 times r outer of the thin-walled tube. So 2 pi r is the circumference, and basically what we're doing is we're cutting it down and we're folding it out, and we're saying it's just a circumference times a rectangle, right? So it's one side of the rectangle is the circumference, and the other side is the length. Anyway, you get what I mean. So let's just pop that in there. 2 times pi times 0.05 gives us 0.31. Well, of course it does. 0.31416 r outer of the thin-walled. So this is how our areas are going to do times. Of course, that would be squared, right? So if we compare these, we're going to see that I've got 3.14, right? I just want to make sure the thin-walled, yes. I'll tell you what, let me just check something and I'll be right back. Okay, sorry about that, but I just wanted to make sure. So I just want to do the cross-sectional area of the thin wall, but now what I want to do is I'm going to substitute in for our outer of the thin wall tube squared is going to be the 1.7 r outer of the thing, so I can compare the two, right? We've got, I'll use my red pen, we've got one of the areas right here, don't we? Pi r squared. Got one of those areas right there in terms of the outer radius of the solid shaft. So I want the rest of these in the same terms of the outer radius of the solid shaft. So I've got 0.31416 times 1.7 squared equals 0.9079. 0.9079 R outer of the solid squared. So we can compare apples to apples, right? So 3.14, 0.9079. And then let's do the same thing for the hollow shaft. So if we do the hollow shaft, but instead of in terms of the hollow shaft's outer radius, we use the solid shaft's outer radius, and we see the conversion factor here, it's 1.19. So 1.131 times 1.19 is, have I got that right? Did I do this one, 0.31, yeah, 0.314 times 1.7 squared. Yeah, I think that's right. All right. Well, let's do this one then, just a second. So I'm going to switch this from 1.19. So 1.131 times 1.19 squared gives me 1.601. Okay, so 1.601 R outer of the solid squared. I hope they squared that. Did I do that? 0.314 and then a 1.7. I'm sure I squared the 1.7. I must have. And so if we look at these cross-sectional, areas as compared to one another, let's do 1.601, or just excuse me, 1.601 divided by 3.14159 is 0.51. So the area of the hollow equals 0.51 the area of the solid shaft. Huge, isn't it? Isn't that huge? We basically have done the same job with this, but we've used half the material. Half the material, right? You get a promotion when you come to your boss and say, hey, I can do the same job with a hollow rod as I could with a solid rod, and I'll save half the material costs that we have. And then, of course, the guy right behind you, he says that the cross-sectional area of the thin-walled tube is, let's just do that, 0.9079 divided by 3.1, oops, wait a second, excuse me, 0.9079 divided by 3.14159, and that's 0.288. So let's say 0.29 the cross-sectional area of that. Isn't that incredible? That's right. That's the problem I wanted to do for you, to show you how this all works together so that you can design and that you can use dimensional analysis. Really, that's what I used here. I didn't even tell you. It's like the punchline at the end of the lecture. We've been using dimensional analysis the entire time. All right. I hope you enjoyed this lecture. I always love giving this lecture. On to power transmission in torsion rods. That's right. You're going to start looking at torsion rods that are feeding generators and feeding propellers that are making ships go. That's our next lecture.